Hi, hi. Am I audible? Yeah. Okay. So, hi, I'm Siddhant, and today we are going to address the very important question we have been dodging for a lot of time, and that is where are the missing gamma rays? So, just to prove that I am a serious researcher, this is the alternative title talk. So, what we are going to look for is the search for high energy gamma ray emission from South Pole Telescope selected galaxy clusters. These are the two paper on which the talk is based on. For complete list, you can just check the arcade. The motivation is that galaxy clusters, as it has also been shown here, has been observed in a lot of wavelengths, in almost all except for gamma rays. The detection of galaxy clusters, especially MEV to GeV and above, is still an open question. Okay. So for our analysis, we use the state-of-the-art Fermi lab, which works on. We use 15 years of data almost. One important point to mention here is the point spread function. As you can see, we kept the lower limit at 1 GeV because the point spread function was quite large as we go to lower energy, so we avoided that. We also we used the maximum likelihood analysis and model the background. That was all basic. One important thing I want to mention is the test statistic, which has not been mentioned much here, and it is basically a comparison of the likelihood of a source which is being present there, which if it is not, and it follows a chi-square distribution for 1 degree of freedom. It also has a gamma ray burst monitor, but we are not going to address that. Okay, so this was just from 1 year of the large area telescope. So yeah, so there's a lot of discoveries which have happened because of Fermi, but galaxy clusters are still an open question. The data set we used was the South Pole Telescope selected galaxy cluster because it is a mass limited catalog, the details of which have already been talked by Dr. Brad, so I won't go into the details. Okay, now the white marks here are those 300 clusters which we searched for individually one by one, while the bright diffuse is your diffuse ray through the Milky Way, right? So what we found is one of the cluster, which is being shown here, shows a very definitive 6 sigma around TS37, which is very high gamma ray emission coming out right around the cluster center. You can see the mark there. This particular cluster is also coincident with Able 3667 cluster. When we plotted the spectral energy distribution plot, we found that all the energies were less than 10 GeV, and beyond 10 GeV we found the upper limits, and the power law fits really well to it, although the best fit spectral index was quite high, which is minus 3.6 what we found. Okay, here there are certain points. So while this result was important because what I know from apart from coma, I think this is the second cluster from which such a high emission was being observed, right? But so one is the redshift, like it is very close. So when we did this analysis, we sorted it out by mass per redshift. So the higher mass in the nearest clusters we studied first, and then as we go beyond. But the important thing is that we found 6 radio sources in the 0.2 degrees of the location where we found the highest emission from. Now this basically dampens the result a bit because it says that whatever the emission of the gamma ray emission which we are getting off could also be because of those radio galaxies and not because of the intracluster medium or something happened there, the plasmas. So yeah, so the follow-up work would be to create a radio template or something like that, and then search for the emissions. We also found 7 other clusters between 3 to 5 sigma detection. Okay, yeah, so that was the first work. The second work what we did was, we took this 300 galaxy cluster sample, we removed those 7 clusters where the emission was greater than 3 sigma, so that it does not affect the overall sample, and then we did the stacking analysis using 16 years of lab data. And okay, yeah, so the process was not very, it was simple. So what we did was, we did a joint likelihood analysis to include all the point spread functions so that it does not degrades, and it is a maximum sensitivities there. We fitted it using power law spectral model and kept the normalization and index free, and varied the photon flux and index. Okay. Yeah, now this is interesting. What we got is when we stacked 293 clusters, we found that there's a very high emission. As you can see, the TS goes around 70 or something. That shows very high energy, like when we stack those clusters. And this is for 2 degree of freedoms. And this is for all those clusters whose individual TS were less than 3 sigma, but when you add those up, the TS goes high. The best fit index we got was around minus 2.6, which was consistent with hadronic emissions. Then we plotted the maximum TS as a function of number of stacked sources. This is as per mass divided by redshift. So the more massive nearby ones were stacked first and then as so on. What we saw is that it's almost a linear trend, which shows that this could be very well dominated by few clusters where the AGN is causing a high energy emission. So what we did was we removed all those again clusters where the emission was between 2 to 3 sigma, and then for any cluster where it's less than 2 sigma, we again did the stacking. There were 170 such clusters. Now what we got was more consistent with the previous result, and also so what we got is the maximum TS of around 9, which is mild detection, mild significance of around 2 to 3 sigma. The index value is minus 2.5. Okay, now this plot here. So this plot shows that could it be diffuse gamma ray, because this is an open question, right? Because CR proton should be there, and those CR proton should produce gamma radiations in the MeV to GeV ranges. Now the plot we got shows that it increases because of the nearby massive clusters, then it kind of plateaus. Yeah, and it could be because of proton-proton interactions happening in the cluster. This is one of the earlier paper by Huber et al. In 2013. What they got and what we got, so they did a 53 cluster analysis. We did a 170 cluster analysis looking at different parts of the sky. But yeah, so hadronic gamma ray emission could scale as m to the power 2 by 3, so depending on mass. So as the equation shows below, that cosmic ray proton, when interacts with the intracluster media proton, it should produce neutral pions, and which should decay into gamma plus gamma, but that gamma is missing and we don't know where it is. So could this be one of the signals, one of the results? Although this is very mild, this is just 2 to 3 sigma, so it is very consistent with the background emission also. Okay, there was some recent other related works which happened in recent years, because for a long time it was just not there. There was a paper in 2025 by Uri Keshet where they found 4.7 sigma significance from stacking. It was an independent result, like stacking, but they were doing it at the same time, and we later corresponded, and it kind of validates the stacking results, or kind of like the search process. There was also a recent talk at ICRC by Mattia Di Maro where they found the TS of around 20, again mild significance. There were earlier papers by Ackerman and Adam. What that says basically is that maybe we are near to resolving it, maybe we need a better sensitive instruments, but in the last few years we have got consistent results where stacking. One more important point which Uri actually argues was that the PSF, the point spread function of Fermi-Lat, basically degrades after 2016, so that basically reduces the quality of the data. So maybe we can do a follow-up to look after that. Okay, so the conclusion is we found one of the cluster Able 3667, we found definitive sigma, like gamma ray emission coming out from that 6 sigma, but the problem is there are 6 radio sources right there, and it's very difficult to know where that emission is coming from. Like it is not easy to know where the emission is templated. And the other one was the stacking result, where we did the stacking of the clusters with minor, mild significance, and when we added up all of those, we found significance of 2 to 3 sigma, which could be hadronic gamma ray emissions, but it is still very mild and not a 5 sigma detection as we hope it could be. Yeah, thank you. Yeah.
Okay. Any questions?
Hello, I have a question about your low TS staticity sample. So you mentioned that it is consistent with the hadronic.
Sorry, yeah. Okay, so this one, right? This one.
Later one.
Yeah.
Yeah, this one. So it's consistent with hadronic. So I just wonder, how this particle be isolated to this high energy.
Okay, so this is not like we can't say for surety, like we haven't modeled the hadronic emission to know. I think we need to do simulations or something like that to know that whether it is exactly coming. I think there's a paper by Mattia Di Maro where they did a simulations. But yeah, so what happens is because in that clusters the proton and electron are protons are at very high energies. Those CR protons should interact with the intracluster media protons and produce neutral pions, which is theoretically valid, like it is already there, that it should be there, and those pions should decay into gamma radiations. Now the question is that it has been a long time, like the Fermi is there, Comptel has been working in MEV ranges, DAMP has been there, but the diffuse gamma ray is still missing. So there are a bunch of paper which points towards a 2 to 3 sigma, but I think we need higher sensitive instrument. Did I answer your question?
Other questions?
Do you have any information about the physical characteristic or like the relaxation, especially of the cluster where you detect gamma ray emission? Because if you say that this is coming from mostly the intracluster medium, maybe there will be more interaction in the medium where there's.
So one thing I forgot to mention and which is relevant to I think your thing is, so that paper, so the first cluster Able 367 Meerkat paper is there on archive which did a complete wavelength analysis, and they found that this particular cluster is a merging cluster where a lot of high energy emission is being produced because of that. So yeah, a lot of that is could. Some of them has AGNs which causes the emission, some of them are merging clusters, a few of them could be intracluster medium or diffuse gamma rays, but it is very difficult to separate it, like it is very difficult to point it out that how different they are. But yeah, for this one, Meerkat did a really good study at that archive paper.
Thank you.
Sure.
Yeah. For interpreting your statistical measurements, are there any quantitative predictions to compare? Any simulations or some analytic?
Okay, so from simulations, so while we haven't done the simulations, there has been some work by Mattia and others where they found 3 to 4 sigma detections using, there's a open source software called Minot, which can be used to do the cluster dynamics. So there's everything from hydrodynamic simulations to magnetic fields and everything, and then you try to look out for gamma ray signatures using those simulations. So they found mild significance, but a lot of that is, so for example in Mattia's paper they found that their sample contained coma, and coma cluster we all know had a very definitive gamma ray emission coming out from it, so it dominated a lot of it. When they removed the coma, the significance dropped a lot, so they could not reduce that, oh it is a definitive signal. But yeah, there have been simulation works. Yeah.
Thank you. Any other questions?
Yes, it might be related to your final comments. So I was wondering, can you explain a little bit more how to remove the contribution from the radio galaxy? Because as you can explain, coma is also having some radio galaxy, but a gamma ray.
So yeah, it is actually quite difficult to point out that whether the emission is from intracluster medium or AGNs. Maybe simulations, like if you can create templates and then do something like that. So one of the work which we tried to, like we will further try to do, was to create a radio template and see the radio emission. And so if, because radio galaxies also contribute a lot to the gamma ray reason. And then one of the other work which I have not mentioned here was dark matter, because dark matter induced gamma ray is also a possibility. We did not found the signal, but we did the analysis, we created dark matter templates, and then we looked out for signal. So yeah, but it is tough, like it's hard to say.
Thank you. Thanks again for speaker and let's move on.